So if you remember yesterday, Werner was the first one to postulate what are coordinate compounds, how do they behave, like why do they exist and all that, right? He just explained the existence of coordinate compounds. He just told that, okay, metal has, a primary valency and a secondary valency, and that's how this bonding is taking place. But he was not able to explain anything else beyond that, like what is the structure like, what is the shape of the molecule, and why, he could not explain the other properties, where does that color come from, what are the magnetic properties and all of that. He was simply mentioning, okay, why do we have such a thing called coordinate compounds, how are they different from ionic and covalent. So in order to explain the rest of the things, we have so many different theories that are put up. The main ones we look at is valence bond theory. Do you guys remember this from last year, VBT? It's gonna be pretty much a rehash of like the same thing with hybridization and all of that. One step above this, we have crystal field theory. So CFT. And then further, like as people got to know more about atomic structures and molecular structures, bonding, like as the developments have taken place, you also have ligand field theory, LFT, and you have molecular orbital theory. For us, like at the grade 12 level right now, we'll only be focusing on valence bond theory and crystal field theory. This is what we'll be looking at. We're not looking at ligand and MOT like right now. Okay, so we'll start off with valence bond theory, VBT. It's very, very similar to what you had in your grade 11 to explain other normal like covalent uh, compounds. Very similar to that. Okay, so according to this theory, the first point, what it says is that the central atom or ion, whatever, like obviously ion comes from that atom, central atom or ion can use either, it will use either the n-1d, ns, and np orbitals, or it can use, it's going to use the ns, np, and nd orbitals in the bonding. Like how does this use them? So it's going to use these for hybridization, that whole thing again. And the rest of the concept follows the same concept as hybridization. So once that hybridization happens, you get, like to yield, a set of equivalent symmetrical, like all in all terms they're pretty much equal, like ns, nd, like spd orbitals all have different energies, different shapes, everything, right? But after hybridization, all their energy levels will be equal, and all their shapes will be pretty symmetrical. So they give like yield a set of equivalent hybrid orbitals. Okay. So these hybrid orbitals are the ones that participate in bonding of definite geometry. So this is where your tetrahedral, square planar, and octahedral is coming from. Okay. Now a little bit of nuance in this, like so basically, when does it use n-1d, nsnp versus nsnp nd orbitals? Now, which specific orbitals it's going to use? This depends on the availability of empty orbitals that it can use for hybridization, and the requirement also, like how many bonds is it forming? Is the coordination number 4 or is it 6? All these factors. So it just depends on the availability. So availability and requirement, how many orbitals do you need for hybridization? Okay. So we look at some examples, will start making more sense. We look at different cases. When is it n-1d and when is it nd? So that difference will get clearer. So what happens when after hybridization takes place is the next step. So these hybrid orbitals are the ones that overlap with the ligand orbitals where the lone pair of electrons are there. So the hybrid orbitals overlap with ligand orbitals containing electron pairs. Read on it. Okay. So we'll take an example, like one example, and then we'll see like what geometry for what hybridization, all those other details. So for example, if you're looking at CONH3 taken 6 times, 3 plus. Okay. So let's see what sort of hybridization and what sort of like what will happen in this case. So what is the electronic configuration for cobalt? We'll start off with like what is the atomic number for cobalt? So cobalt is 27. So electronic configuration क्या होगा इसका?
1s2, 2s2, 2p6, then 3s2, 3p6, 18,
Remember Morse diagram.
4s2 and 3d7.
यहाँ पे NH3 is neutral, cobalt is at 3 plus. So CO3 plus will like lose 3 electrons. So we have 18, like 3p6 तक यही होगा. And then 3 electrons if it loses, will it be 4s2 3d4?
No, first from the s1. So maybe 3.
Yeah, 4s निकल जाएगा. उसके बाद we will simply be left with 3d6. Okay. So यहाँ तक 3p6 argon noble gas configuration, all of these are settled. They will not take part in bonding. So it's only the 3d orbitals that we have, like 3d electrons that we have to focus on. So D has 5 orbitals, 6 electrons distributed in this way. Okay, so what happens is now all these electrons are unpaired, right? The like you have 3d orbitals, then you have 4sk empty orbitals are also there. So this is 3d6, and then you have 4sk yeah, single one thing, and then 4p has this like 3 orbitals that's like also lying empty, right? Now cobalt is bonded to 6 ligands, 6 ammonia amine ligands, which means it needs 6 hybrid orbitals in this situation. Okay. So what happens is when it has to bond with the ligand, all the unpaired electrons get paired up. So these electrons will align themselves, like this is unchanged. Then the 3D electrons will rearrange themselves like this. 6 electrons matlab 3 pairs. So now it has 2 empty 3D orbitals plus 1 4s orbital plus 3 4p orbitals. Okay, so these empty orbitals will together hybridize to form 6 D2 sp3 hybrid orbitals. So the hybridization in this particular compound is D2 sp3. So in this situation, you can see that hybridization we're getting from 3D, 4s and 4p orbitals. So in this case, because it required 6 hybrid orbitals, matlab in order to get 6 hybrid orbitals, it needed to invest 6 individual orbitals. So that's why it gave like the 2 of the 3D orbitals and the 4s and 4p orbitals. They all together hybridized to form 6 equivalent D2sp3 hybrid orbitals. Now, because they're all equivalent, the way they arrange themselves, perfectly symmetrical. So all of this ISCA shape will be octahedral. And now it is ready to overlap with ammonia, like with the ligand. So ammonia, if you remember, ISCA shape is you have nitrogen and you have, it's a tetrahedral shape. Like you have 3 hydrogens here. And it has 1 orbital that has like the lone pair of electrons. So this particular orbital from ammonia will overlap with, like there's 6 of these, right? So each one will overlap with each of these hybrid orbitals to form your coordinate complex. Okay, so this is what valence bond theory is stated. Okay. So yeah, so there's different types of hybridizations possible. Like I'll give you guys the table for this. So depending on how many ligands, what structure and all of that. So we have different cases. So coordinate number, then what is the hybridization? And what is the shape? Shape is same as what you guys learned in BBT and in like VSCPR. So that's pretty straightforward. Some of the hybridization, like that part, will be like slightly new to you guys. So that. So coordination number agar 4 hai, there's 2 different cases of hybridization possible. You have your regular old sp3, in which case you get a tetrahedral shape. But if you have dsp2 hybridization, you get square planar. And if you have coordination number 5, if it needs to form 5 bonds, you have sp3d. This is trigonal bipyramidal. And if it is 6, you have, again, you have 2 different cases. You have sp3d2. And you may have d2sp3 also. In this case, it's the same structure. Both of these are octahedral. I'm probably gonna need one more session for this chapter. Okay. Finish noting down this. You finish writing down this stuff, right? Okay. Now, I don't know if you've like gotten this doubt yet or not, but how do you figure when is it sp3, when is it d2, dsp2? How do you figure when is it sp3 d2, when is it d2 sp3? In this case, I just told you that oh pairing takes place इसलिए d2 sp3 है. But the same cobalt, when it is forming a complex with fluoride ions instead of ammonia, then it undergoes sp3d2 hybridization. Same oxidation state, same cobalt, same number of electrons, but ammonia ke saath it's d2sp3, fluoride ke saath it's sp3d2. Now you're just taking my word for it, but how do you figure out in which case what is what? That's a major drawback with valence bond theory. So with valence bond theory, because it was one of the first theories to explain the structure and all that, they sort of reverse engineered it. Okay. So for this, I need you guys to recall the concept of magnetism. Do you remember paramagnetism, diamagnetism? Paramagnet, like when is something paramagnetic? When is something diamagnetic?
Like not when wala part, but like paramagnetic was the one which shows the magnetic property and dia does not show.
Correct. Now, what is the criteria? Like from the electronic configuration, you can figure out whether something is going to be paramagnetic or diamagnetic. You guys remember that? Like it's related to electronic configuration. Yeah, there? No?
We had done that whole diagram of the electron bonding and everything last year.
Yeah,
To
molecular
figure.
and all that, right?
Yeah.
Yes. Yeah, you remember you did it, but you don't remember the specifics.
Yeah.
Yeah. Sanskriti, what about you? Chemical bonding chapter mein tha.
Ma'am, I don't remember it.
Okay, no worries. So if you have unpaired electrons present, so molecular orbital theory mein, there also you place electrons in molecular orbitals. Even in element, it's the same concept. I think structure of atom mein bhi tha. So suppose you come across an electronic configuration, जिसमें there are unpaired electrons. Then they will like react to a magnetic field and we call them, we say they are paramagnetic. But if all the electrons are paired up, so all are paired, then they will not react to the magnetic field and we say they are diamagnetic. See? So yeah. So what, like for valence bond theory, like how did they figure out which one has which hybridization is first, like they take a particular complex and they measure the magnetic moment. So magnetic moment, you can measure it by this formula, root of n into n minus 1, I think. So where n is the number of unpaired electrons. So like if it has any unpaired electrons, it's going to show some sort of a magnetic moment. It's going to react to a magnetic field. So by measuring how much it is, like by measuring the magnetic moment, you figure out how many unpaired electrons are there. And based on that, you can figure out, okay, what is the electronic configuration. So in this case, like if you take this hexamine cobalt complex, it's not going to show any magnetic moment because all its electrons are paired up. Like experimental basis pe, they figured out that it doesn't have any unpaired electrons, all its electrons are paired. So isliye they figured ki okay, cobalt oxidation state is 3 plus, there is no magnetic moment there, which means sare electrons paired up hai, this should be the electronic configuration. Now based on this they figured okay, two empty d orbitals s and p3, इसलिए इसका hybridization is D2sp3. Okay, so that's kind of how they worked with like that's how kind of how valence bond theory worked. So we had to note down the points. The first step is like get the electronic configuration based on the magnetic moment. So magnetic moment say you'll figure out whether the electrons are paired or unpaired, or how many are paired up, how many unpaired, that way. Like indirectly. So you'll get the number of unpaired electrons. So from that you arrange it in your orbital to figure out what it is. And the oxidation state. So oxidation state will tell you directly कितने electrons are. Cobalt 3 plus है, इसलिए you figured it was D6. Otherwise it would have been D7 that way. Okay. Then you check the number of ligands. And then figure out the hybridization from that. And once you've done all of these three, you can get the shape of the molecule. Oh, sorry, shape of the complex. These are the steps. Like if you apply valence bond theory, this is what you have to do. You need to know the magnetic moment first, otherwise you won't be able to figure out just from the formula. Okay, so you have two different types of complexes. So based on the number of unpaired electrons, based on the magnetic moment, you have two different types of complexes. So you have, like, if the inner orbital is hybridized, one type is where the inner orbital is hybridized. So like DSP2 or D2sp3 type. So this will show, like, these are also called low spin complexes or spin paired complexes. Makes sense, right? Like, because all the electrons are paired, the number of unpaired electrons is lesser in this situation. And the other type of complexes are outer orbitals, like where the outer orbital is taking part in hybridization. So sp3d2, for example. So the 4d orbital is hybridized, not the 3d. So this usually is characterized by high spin, also called a high spin complex, or it's also called spin free complex. So it is characterized by a higher number of unpaired electrons. So low spin means all of them are paired. High spin matlab more unpaired electrons. This has unpaired electrons, has a magnetic moment. So examples for both inner orbital is the one that we just saw. So like cobalt, like hexamine cobalt 3 plus, and high spin ke liye similar situation, we say COF6 3 minus. Dono mein cobalt is present in +3 state. The only difference is that if it's ammonia, like forming a coordinate bond with it, all the electrons get paired up, you end up with a low spin complex. If it is fluoride coming to form a bond with it, you get a high spin complex. Electrons are unpaired. Unpaired matlab, this particular electron configuration is maintained. So you have sp3d2 forming, like, in the hybridization. See, you have sp3d2.
But then those orbitals remain with one electron only, not complete as a paired.
Yeah, they remain with one electron, which is why high spin, right? Like the spin is not cancelled by each other. Like plus half minus half is not cancelled. You just have plus half.
That's why they show magnetic properties.
Yes.
Okay.
So that is the difference. Like that's how you can figure out, oh, this is like inner orbital low spin complex, this is outer orbital, because this complex will show a magnetic moment, this will not show any magnetic moment. That's why your first thing, you can get the electronic configuration based on the magnetic moment. So this will tell you whether electrons are paired or unpaired. Yeah. So, but considering like you need to measure the magnetic moment first, you can't like theoretically calculate it based on looking at the formula. So that's where VBT fails. That's why you needed like a better explanation for the shapes and structures. And you also can't predict which one's going to be low spin, which one's going to be high spin. So it fails which elements can form coordination compounds. By this method, even if you take, I don't know, sodium, potassium, there are empty orbitals. Theoretically, it is possible, but you don't find them in coordinate complexes, right? It fails at directional properties. It literally just tells you the shape of this thing. It doesn't give you any more information further than that. And this is like reverse engineered. Looking at a particular complex, you can't predict its properties. By looking at the properties, you're figuring out the shape and everything. That's a huge limitation with VBT. Okay. So the better alternative, like the better theory that has been proposed, is the crystal field theory. CFT. Okay. So CFT, in order to, so okay, like I'll give you the introduction first. So CFT is based on repulsive electrostatic interactions. How is it based on that? It'll get clearer when I start explaining. So it's based on repulsive electrostatic interactions. Like just remember these terms. So there's electrostatic interactions going on. Matlab you have like negative charge, positive charge kind of like interacting with each other, or maybe two negative charges interacting with each other. They happen to be repulsive. So obviously, yeah. So there's two negative charges interacting with each other. That's roughly what it's based on. And crystal field theory is better because it can explain the shape, it can explain the magnetism and the optical properties, like whether it will have a color or not, like all of that, simply based on just by looking at a particular complex. If you know what metal is there, what ligand is there, you will be able to get all of these details. Okay. All right. So to get into crystal field theory, where are these electrostatic interactions based on? We need to get back to the metal atom. So that means we'll have to look at the structure of that atom itself. Do you guys remember how the d orbitals are arranged? Do you guys remember the shape of the d orbitals? I know it was like over a year ago, last year, पढ़ा था.
That XYZ thing.
How many total d orbitals are there? There's
5.
5. So in a normal neutral atom, like without any bonding or anything at all these 5 d orbitals will have equal energy, right? They are called degenerate. Degenerate simply means equal energy. They're all equal to each other. So how, look at the shape of these orbitals. Do you remember the shape of the d orbitals, how they're arranged in space? I'm just gonna draw 5 of these. Or do you remember the names at least, like theory? Which are the 5d orbitals? No? It's gonna take a long time. Okay. So the 5d orbitals, you have dxy, dyz, dxz, and then dx square y square and dz square. It's like, is it refreshing? Yeah,
Yes.
after talking about it. Okay. I'm gonna quickly switch to this. Where did I open it? Ah, here it is. Yeah, handy dandy shape of the orbitals. Here you go. Okay, so dxy, dyz, and dxz are very similar to each other. They're like this butterfly shape, double dumbbells. The only difference between them is where in the 3D shape they are located. Like, since you've now done 3D geometry, I'm hoping that you guys can imagine at least, 3D things. Okay, so I'm gonna look at dxy. Here you go. Dxy, you can see. So it is located in between x and y axis. So z axis में कुछ है नहीं. Once it stops spinning, yeah. So you have x axis and y axis, and it's located like in the quadrants between the x and y axis. Okay, got the visual? Now dyz and dxz are also the exact same thing. The only difference is that they are located in between the different axes. So dxz is located between x and z axis, but essentially it's the same thing. And dyz also is the same thing. It's just that located between the y and z axis. Okay. Like x axis पे कुछ है नहीं. Like if you see, this is y axis, this is z axis. It's located in between them. Okay. So these three are very similar to each other. They're just, one is aligned this way, one is aligned this way, and one is aligned in this direction. These three directions. But all in all, they're like between the axis. They're not like, they're at 45 degrees to the axis, aligning. Dx square y square, now that is slightly different. The shape is the same, but it is aligned along the axis. So it's not in the quadrants, it is on the axis itself. Like you can't see where x and y axis are there because these lobes are covering it up. Okay. And dz square is also along the axis, but on the z axis side. And there's like a tire on the x and y axis. But whatever the case is, it's not in the quadrants, it's like along the axis. Okay, so just remember that because that is important. That will come into picture when we talk about it. So these three are of a certain kind. They are all like in between the axis. These two are along the axis. So x square, y square is along xy, and z square is like along the z axis. Correct. Here's a situation. So default metal atom all orbitals are equal in energy. Now, if we take the metal atom, so by default, it is going to have a certain energy level. It's going to be at a certain energy level, right? Access to the energy. So initially, all 5 of them are at a single energy level when the metal atom is just chilling. Now, if I surround this metal atom by a negative charge, but that particular negative charge is equal in all the directions. Okay, like imagine I'm surrounding it by a sphere of negative charge. Then the orbitals, like these are electronic orbitals, there are electrons present in them, right? So negative charge on the surface of the metal atom and negative charge surrounding it, there's going to be repulsive forces between them. So if there's like repulsion between them, higher in energy, मतलब थोड़ा potential create हुआ है, like there's potential energy there because of the repulsion between them. But still, because it is completely perfectly symmetrical, it's a spherical sphere of charge. So in all the directions, it is equal amount of negative charge, negative energy, which means that all these 5 d orbitals will be at a higher energy level, but still all of them will be equal. They're still, like initially they were degenerate. Here also they are degenerate. They're equal in energy. Just that it's a higher energy because they are surrounded symmetrically, like on all sides. Okay. But this is not what happens in reality. In reality, what happens is the metal atom is surrounded only at certain points. It's not surrounded spherically by the negative charge. The ligands approach it either tetrahedrally or octahedrally, right? So octahedrally matlab you're going to have negative charge only on the axis. Tetrahedrally matlab you're going to have the negative charge only in between the axis, right? So depending on whether the ligand is approaching tetrahedrally or octahedrally, the different d orbitals will face different levels of repulsions between, like from the ligands, from the negative charge. So depending on how the ligands are approaching, whether they're approaching on the axis like octahedrally or whether they're approaching tetrahedrally, like between the axis, different d orbitals are going to, like some d orbitals are going to face higher energies and some other d orbitals will face higher energies in different situations. Okay, so this is like the crux of it. This is the basis for CFT. So because we have 2 different cases, whether ligands are octahedral or tetrahedral, we have, like we'll also discuss this whole theory as 2 different cases, octahedral or tetrahedral. Okay. So roughly speaking, like just as a preview, I just tell you guys, if it is approaching octahedrally, in the case of octahedral complexes, because it is on the axis, which means dxy and dz, so dx square y square and dz square will have a higher energy, like the orbitals that are on the axis. And